Hello viewers, welcome back to class. I'm super excited to welcome you guys back to class again. You're welcome to Master Builders Online Academy. If you are new in this channel, do consider subscribing to our channel and ensure you turn on the post notification bell for more exciting videos. Guys, don't forget our policy. Anytime you are set to watch and to learn new concepts from Master Builders Online Academy, do not welcome any form of distraction. This is for your own good. And secondly, anytime you are set to watch and to learn new concepts from this channel, ensure that you do not skip any part of video, because every bit of this video is release of principles. So when you skip principles that works, you may be stranded as you go along the way. So the only way you will not be able to skip relevant principles is to ensure you do not skip this video. So watch the video from the starting point to the finishing point without skipping any part. This will do you really good. Then finally, if after watching this video you do not understand some concept, guys, you have a singular opportunity to replay the video over and over again until it sinks into your mental capacity. Then if at the end of replaying the video over and over again, guys, you still have questions to ask, that's why we are here. Don't hesitate, just go down to the comment section and make your questions known to us. We will answer your question and give you befitting solutions to whatever problems that you drop at the comment sections. Now, also, don't forget that this lesson is mainly for structural engineers, designers. Okay? So, on the board we have design of reinforced concrete beam, and this happens to be the very first problem that we have. We are asked that the ultimate moment to be resisted by the section shown below is 180 kilonewton meter. Now, we are asked to determine the area of reinforcement required and the overall depth. Two things. Determine the area of reinforcement AX required and the overall depth H of this section, given the following characteristics, material strength as what we have on the board. Now, for us to be able to design any structural element very well, and for you to be able to solve any word problem question very well, the first thing that you must do is to list out the parameters, which include the given and the unknown parameters. This will help you get the relationship between the known and the unknowns. And when you get the relationship between the unknown and the unknown, then you'll be able to trace the actual formula that will help you provide the necessary solutions. So now let's quickly start by extracting out all the given parameters, both known and unknown. Now we have moment at 180 kilonewton meter, and this is equivalent to 185 multiplied by 10 raised to the power 6 Newton millimeter. So anytime you are solving with moment in design, you must convert to this unit, Newton millimeters. And to convert from kilonewton meter to Newton millimeters, you simply multiply the given value by 1 million, which is exactly the same as 10 raised to the power of 6. Now, the next parameter that we have here is area of steel. Area of steel, AX, and this is unknown. Then we have overall depth. And this is equally unknown. Then we have the characteristic material strength, F of Y is equal to 460 Newton per millimeter squared, and F of Cu is equal to 30 Newton per millimeter squared. Then we are given that D is equal to 440 millimeters and B is equal to 260 millimeters. You see, with what you have here now, nobody stated that this 440 millimeters is effective depth. But from the lesson we had before, we said that from the top of the compression zone till the middle of the tension reinforcement, that is what we call the effective depth. So the effective depth is what? The distance between the center of the bottom reinforcement and the top surface of the compression section. Are we there? So we understand by those principles that this guy is the effective depth. Now, we have successfully extracted all the given parameters. Now, this question requires us to provide the area of reinforcement. That means we have to design against this moment. And for us to be able to design against this moment, like we said earlier, from the procedures of solving either singly reinforced or doubly reinforced, that the first thing that we need to do is to obtain the design load. And you obtain the design load when the loadings are given. Then after successfully obtaining the design load, the next is to obtain the design moment. And now from this question, we see that the design moment is already given. That means we start from that step. Assuming this question came in such a way that we have the loadings, then we will start by calculating the design load. But now that we already have design moment, our analysis will start from step 3, no longer step 1. So if we are starting from step 3, what do we do? Now that we know the moment, I want to start from step 3. What is step 3? Once the moment is known, the next thing you do is to test run whether you are designing this beam as a singly or as a doubly. And that is the reason why you calculate for K. So we have that K is equal to what? M over F of Cu BD squared. So I will quickly substitute into this equation 185 multiplied by 10 raised to the power 6 all over 30 multiplied by 260 multiplied by D is 440 all squared. And when I compute the value of K from here, we will have this to be 0.12 approximately. This is what we have. When you substitute into this formula and you compute this out, simplify this, this is the outcome. Now, if this is what we have, this value is 0.12. And we said that anytime the value of K calculated from the design moment is less than 0.156, we should design as singly reinforced. Now, we have that since K equal to 0.12 is less than 0.156, then design as singly reinforced. So you see the condition now. You must ensure that you calculate out the value of K. So that if we try also to calculate MU equal to 0.156 F of CU B this way, you will discover that the moment you will obtain from here will be more than 185. And these are the controlling factors I mentioned earlier. It is either K is less than 0.156 for you to design the beam section as a singly, or the ultimate moment of resistance to be offered by the concrete is more than the moment induced or that is being induced on the concrete. So this is the moment that is being induced on the concrete or that is acting on the concrete. And the concrete moment is expected to be higher than this moment for this section to be designed as singly. Now this factor has already proved that when we calculate for the ultimate moment of resistance of the concrete, it will definitely be more than 185. This has already proven that, which you can test run. So for us to design as singly, it is either K is less than 0.156 or the ultimate moment of resistance in concrete, which is Mu, is greater than the applied bending moment, which we were given. Now if this is taken, the next is to calculate the lever arm factor, which is step 4. So we have lever arm factor LA is equal to 0.5 plus the square root of 0.25 minus K over 0.9. And from what we have here, we substitute the value of K, then we have LA is equal to 0.5 plus the square root of 0.25 minus K is 0.12 all over 0.9. So when we simplify this, we have this as 0.84. This is the value that we have. Now that we have successfully obtained the value of the lever arm factor, the next thing we will do is to obtain the lever arm itself. And we know that the lever arm is being controlled by the lever arm factor. Now, if this is true, therefore, what is the lever arm? We said that the lever arm, which is Z, is equal to lever arm factor multiplied by effective depth. And also, we mentioned earlier that the lever arm factor has certain limits. It has upper limit and a lower limit. We said that the lower limit is 0.775, while the upper limit is 0.95. And we said that when the calculated lever arm factor is less than 0.775, we will make use of this. But if it is greater than 0.95, we will make use of this. Now, if it is greater than the lower limit, but is less than the upper limit, that means it is in between these two values. Then make use of the calculated value. Now, when we compare the value we obtain from this formula to the standard, we discover that the value is more than the lower limit, but less than the upper limit. It falls within the range, then it is accepted. Then we will make use of the calculated value. These are the conditions that you need to know when you are designing a structure. And that's why I made it clear in our previous lesson and every of our lessons that when you know principles, you become a principal. And when you understand boundary conditions, you will not overstep your boundaries. Very, very important. So there are boundary conditions that you need to know as a designer. Now, if this is understood now, so you now know the reason. If you have seen this before in your textbook and you do not know why they make use of all of these formulas interchangeably, you have gotten it now. So we are going to be making use of the calculated because the value is more than the lower limit and is less than the upper limit. So it falls within the accepted range. Then we have that Z is equal to 0.84 multiplied by what is the effective depth of this concrete? The effective depth of the beam section is 440 millimeters. Then we have 440 millimeters. Guys, when we multiply 0.84 by 440, we will have this as 370 millimeters. This is the lever arm value. Now that we have successfully obtained the lever arm value, the next is to obtain the area of steel. This is where we want to find the very first question, or the very first thing we are asked to find, area of steel, which is AX. So now we have that AX is equal to M over 0.95 FCY Z. Now we substitute the values of all of these parameters here. M is 185 multiplied by 10 raised to the power 6. All over 0.95 multiplied by 460 multiplied by Z is 370, all in millimeters squared. Now when we solve this, our answer becomes 1144 mm squared. This is the area required. The calculated area is what we call area required. Now we need to now make available the area provided. So as an engineer, at this point, you need to get your table. Okay? You need to get your design table for beam so that you can go to the beam table and trace out the area of a beam that is exactly this or more than this. Not less than the calculated, but it should be exactly or more than the calculated. So we'll now go to our table, which will be the next step. We say provide. So now, if this is my table, and this is the beam section, so all I need to do is to trace. I have different types of beam table here, of design table. Different types of design table. So before you pick any of the options, ensure that you read the headings very well. So the first table I have there now is table 3, which is number of reinforced bar in groups. Now, when you are designing structure, the ones that are in groups is either beam column or foundation. For slab, they are area per meter width, and that is the table 4 here. So anytime you are looking for group bars, we are actually looking at beams, columns, or foundations. So if this is understood, now we will go to that section. Now, the first column here is for the bar size, while the first row here is the number of bars. So I can pick 1, 2, 3, 4, 5, 6 till 10. Now let's look out for the value of the area required that we have here. Now we have 1,144. So when I come to this table, I will look for a value that is more than that. Let's come to Y3. For Y3, if I come under number 3, I trace down where I will have a value greater than 1144 is 1470. And when I trace it out, I will have 3Y25. I have that as 3Y25 millimeters. Okay? Now another person can say, okay, no, I wouldn't want to use Y25. I want to use a lesser bar size. Once the bar size, you want to make use of a lesser bar size, the number of bar increase. So when you want to make use of a very high area or a minimum number of what bar, therefore the bar size increases. So when I have increase in bar size, the number of bars reduced. But when I want to increase the number of bar, therefore I will increase the bar size, the diameter. So now I want to increase it. I now decide to use 4Y. You discover that at the end, the diameter of the bar will not be up to 25. Now let's check that out. So if you come to the same table and trace out under 4, if you trace down to under 4, you will see that you have a place where you have 1260. And 1260 is greater than this guy. And when you trace it and you discover that it is under 20, so this will have given us 4Y20 millimeters. So now, in my case, I will prefer. Now, another thing we also consider between the area of this guy and this guy, this one is higher than this by far. Because this is 1470 and this is 11. So if this is 11, let's go for 12. So this is 1144. But the area of this first guy is 1470. While this one is 1260. So between this guy and this guy, the one that is closer to this is this. So it shows that this one will be more economical than this. So if I go with this, it's still okay. If I equally go with this, it's okay, but it is preferable when you go with the area that is very close to the area provided for economical purpose, so that you will not have over design. So therefore, at this point, we will simply say provide 4Y20 millimeter bar, and the area of steel here is equal to 1260 mm squared. Area of bar is equal to 1260 mm squared. This is the area provided. Like I said, there is a criterion to test run whether the area provided is adequate. Okay, so to test run, it is either the value is greater than this or less than 4.0. So what you do is there is a formula to test run this. Okay, and that formula you find it in the material. Okay, now let's go. Now we have successfully provided the answer to question number 1. Now for question number 2, we are asked to find the overall depth, and this will be easy for us to obtain. Now I gave us the relationship between effective depth and the overall depth area. So now let's look at that. Now question number 2, we are asked, Roman figure 2, overall depth H. I was saying earlier that overall depth is equal to D plus C of 5 over 2 plus C, where D is the effective depth, this is the size, and this other guy C is the concrete cover. Now if C is the concrete cover, therefore, and in this question we're not given concrete cover, so you can pick or assume a concrete cover that is within the criteria. You can use 1 inch, which is 25 millimeters. You can use 30 millimeters. You can use 35. You can use 40. So it's a matter of choice. All right. So in this case, now that we are not given, let's assume, but assume at least 1 inch, at least. except you are given, you can make use of the given value. But if you are not given, assume at least 1 inch. So therefore, we assume that the concrete cover under severe condition, assume concrete cover C to be what? 30 millimeters. Okay, let's use 30 millimeters. You can use 25, like I said, 1 inch. Then we know that the bar, from what we calculate, we provided 4 wide 20. Don't forget that 20 is the bar size. That's the diameter. Then you pull down 20 millimeters. And we were given D already, so H therefore become 440 plus 20 over 2, which is bar size over 2, then plus 30. Now, final answer becomes 440 plus 10 plus 30. And this would have given us what? 480 millimeters. So this is the overall depth of this session. Now, one thing you need to understand that in design is that there is no structural design book where you will find answer at the end of the textbook. No. Why? Because of the assumption, various assumptions that different structural engineers provide. You will definitely not have the same result, but you ensure that the outcome is within the acceptable limits. You work with the criteria BS 8110. It must be within the criteria. So if I have this and another person assumes this 25, then if you substitute 25 there, you have this as 875 millimeters. Someone that have this, you are still very, very correct. So in design, you are not expected to have the same result, not like quadratic equation or general mathematics, whereby if everybody solves, no matter the steps you take, you must arrive at the same place. No, for design, it is not so. Okay, but you must ensure that the value you have is within the confines of the limit provided by the codes of practice. Now, if this is understood, therefore, this is the answer to this question. Like I said, design is very, very simple, but you need to understand the principles. You need to understand the boundary condition. You need to understand the BS code very well, so that you will know some certain principles that works when you are experiencing some certain failures. Maybe when you want to check for deflection, you want to check for cracks, you want to check for shears and others. This must be put into consideration. So guys, don't forget, when you know principles, you become a principal. And equally, when you understand boundary conditions, you will not overstep your boundaries. This is very, very important. So any course you are dealing with, ensure that you know the principles that are working. Now, if at this point you are yet to subscribe, please consider subscribing to this channel and ensure you turn on the post notification bell for more exciting videos. So guys, love you. Share this video, like this video, and make your necessary comment. We will see you in the next class.